Our next example is the function space C01. So this is a set of all functions from 0, 1 closed interval into R such that f is continuous. So this becomes a vector space with the pointwise addition and scalar multiplication. So f plus gx is fx plus gx, alpha fx equals alpha times f of x, and this is true for all x in 0, 1, for all alpha in R. So with this we have a vector space. Now every continuous function on a compact interval is bounded and attains its maxima and minima, and therefore we can define the following is well defined. Norm f we are going to define as max mod f of x belongs to 0, 1. Now this is a very simple exercise for you to check that this defines a norm, and therefore I will leave it to you to do it. So the triangle inequality is also very trivial, just as we did it in the L infinity case. Here also we have this. So we want to show that this defines a Banach space. So we take a Cauchy sequence. Then what do you have? For every epsilon positive, there exists a capital N such that for all nm greater than or equal to capital N, we had mod fn of x minus fm of x is less than epsilon for all x in 0, 1. This is what we mean, because when we say the norm is Cauchy, therefore for all x, since the norm is defined by the maximum, this happens for every x. Therefore for every x in 0, 1, we have that the sequence fnx is Cauchy, and therefore it converges. So let us define f of x as the limit n tending to infinity fn of x. So we now have a function from 0, 1 to R. So we have a candidate for the limit of the Cauchy sequence, and therefore we ask the usual questions: is the candidate eligible? So we want to know if fx f belongs to C0, 1 and so that is the question which we have to answer. And then of course if we have that norm fn minus f tends to 0 as n tends to infinity. If we answer again these two questions in the affirmative, then the Cauchy sequence will have a limit, and therefore the space will become a Banach space. So first of all, we have that fn x minus f of x, fm of x is less than epsilon for all nm greater than or equal to capital N. This is what we saw. So you fix n and let m tend to infinity. So fix n and m goes to infinity. Then you have mod fnx minus f of x is less than or equal to epsilon for all n greater than or equal to n, and of course for all x in 0, 1 in both places. So we have that fn converges uniformly to f. This is the convergence in this norm is essentially uniform convergence. So if we prove that f is continuous, then so if f is continuous, then norm of fn minus f goes to 0 by what we have just said, and therefore we would have that we are in the situation of a Banach space. Now we already know from real analysis, I will do it again, that if you have the uniform limit of continuous functions, then it has to be continuous. So I am just going to reprove that fact. So let us take any x naught in 0, 1. Now given any epsilon greater than 0, there exists a delta such that you have that mod fn of x minus fn of x naught is less than epsilon for all mod x minus x naught less than delta. In fact, this delta is independent of x naught because you also have uniform continuity on that interval. Anyway, that we do not do. So this is true. So in particular, I am going to do it for n equals capital N. I am going to choose this delta. So now you look at mod fx minus f of x naught. I am going to write this as mod fx minus fn of x plus mod fn of x minus f of x naught, fn of x naught plus mod fn of x naught minus f of x naught. Now what we just saw above, for all x, fn of x minus fx is less than or equal to epsilon if n is greater or equal to n, and therefore this is less than epsilon. Similarly, this term is also less than epsilon, and by the continuity condition we have that this is less than epsilon whenever for all mod x minus x naught less than delta. So this thing is less than 3 epsilon, that doesn't matter, and therefore you have shown that f is a continuous function. So every Cauchy sequence converges, and therefore C01 is a Banach space. So this is the example of a function space. We will see many more function spaces later, so we will leave it at this. So before concluding this on examples, so let me do one final example if you like. So this is how to produce new Banach spaces from old, or new norm linear spaces from old. This is standard in mathematics. We do it all the time. Whenever we have a structure, there are at least 2 different ways of producing new objects with the same structure. One is known as a subspace. So if you have a group, you have a subgroup. If you have a topological space, you have a subspace which inherits the same structure from above. So same way, if you have a norm linear space and you have any vector subspace of V, you put the same norm there, you get the subspace. So this is always true. The other structure is that of the quotient space. So we will give you the example, or we will discuss quotient spaces. So we have that V is a norm linear space, and let W be a closed subspace. So this is important, and we will see in a moment why we want to do it. So then we define the equivalence relation. X is related to Y if and only if x minus y equal to belongs to W. So this defines an equivalence relation, and then partitions V into equivalence classes, and these are called the cosets. The equivalence classes are cosets denoted by x plus W. So this is nothing but the set of all x plus small w, where W belongs to capital W. So the set of all such cosets, so the collection of cosets we call the quotient space V by W. We can give this a vector space structure, namely, so if you have two cosets x plus W and y plus W, then we can define the addition as x plus y plus W. And similarly, if alpha times x plus W, we define as alpha x plus W. We have to check that these are well defined, because if x is equivalent to x dash, y is equivalent to y dash, since W is a subspace, x plus y will be equivalent to x dash plus y dash, and therefore this is well defined. Similarly, alpha times, if x is equivalent to x dash, alpha x will be equivalent to alpha x dash, and therefore this is also well defined. So the cosets can be defined. The operation does not depend on the representative you are taking for the coset, and therefore you can do it. So now we are going to define a norm on this. So we define norm of x plus W in the quotient space. So the I'm denote is by definition again is the inf of norm of x plus W, W in W. So you take all elements of the coset, take their norms and take the minimum of that you are going to define as this. And so we now have to check that this is a norm. And in this case, for the first time, we will have the triangle inequality is not the only one which requires some calculation. So first of all, norm of x plus W, V by W is greater than or equal to 0. That's no problem, because you are taking the infimum of non-negative numbers and therefore it's non-negative. So let us see the second one. So we are taking that x plus, what is the 0 element? X plus W, so should be equal to 0 plus W. This is the 0 element. That means x itself belongs to W. So then it's the 0 element. So if you are taking the 0 element, and if x belongs to W, then you also have minus x is also in W, because W is a subspace. Therefore, norm of V plus x plus W in V by W is less than or equal to norm of x plus minus x, which is 0, and of course this is greater than or equal to 0. So if you have the 0 element, the norm of x plus W is just 0. Conversely, let norm of x plus W in V by W be equal to 0. Then we have to show that this is the 0 element, or in other words, to show x belongs to W. Then this will become the 0 element, because if x belongs to W, that is nothing but the 0 element here. Okay, so what does the definition say? Definition is the infimum of something, and therefore if this is 0, this means there exists Wn in W such that norm of x plus Wn converges to 0, because the infimum is 0, you have that this goes to 0. So this means that Wn converges to minus x. Now W is closed, so this is where the hypothesis closed is important. So this implies that minus x belongs to W, and this implies that x also belongs to W, and therefore we are through. Now we want to show the third property. So if you take alpha x plus W, if alpha is 0, this is a 0 element, so there's nothing to do anything. So let us assume alpha is not 0, and therefore this can be written as alpha times x plus W again. Okay, because if you take alpha x plus W, this can be written as alpha times x plus alpha inverse of W, which is again an element of W. And therefore from this it immediately follows that the norm of alpha x plus W in V by W is nothing but mod alpha times norm of x plus W V by W, because every element here can be written as alpha times something, and you are taking the infimum of the norms. Okay, so now we are going to show that triangle inequality. Okay, so we have to look at norm of x plus y plus w in V by W. So this by definition is the infimum of norm of x plus y plus w, w in W. This is equal to the infimum of norm of x plus y plus w dash, w and w dash in W. Why is this true? Because these two sets are one and the same. For instance, this can be written as x plus y plus w plus 0, and x plus y plus w dash can be thought of a single element. So these two sets are really the same, and therefore the infima are the same. So now, but because of the triangle inequality, this is less than or equal to infimum of norm of x plus w plus norm of y plus w dash, w dash in W. And now this is equal to, so this is a small checking on the notion of infimum from real analysis, which you should do. So this is equal to infimum of norm of x plus w, w in W, plus infimum norm of y plus w dash in W. So this is a small checking is needed, but you should be able to do it. But then this is nothing but norm of x plus w in V by W plus norm of y plus w in V by W. And therefore we have shown that the triangle inequality is satisfied. So V by W, where W is a closed subspace, makes a non-linear space. If V is complete, so is V by W. So if the original space is Banach, then the quotient space also is Banach. So the quotient space inherits the Banach or completeness property. So we have to show that every Cauchy sequence converges. So let us take a Cauchy sequence. Cauchy sequence in V by W. So we need to have a subsequence. Now, given any Cauchy sequence, again this is a property of Cauchy sequences, you can always find a subsequence such that consecutive elements differ by whatever quantity you decide. So there exists subsequence x and k plus w such that norm of x and k plus w minus xn k plus 1 plus w is less than 1 by 2 power k. So this is a property of Cauchy sequences which you should. This, what does this mean? This means there exists yk in x and k plus w such that norm of yk minus yk plus 1 is less than 1 by 2 power k. And this implies that yk is Cauchy. Why is yk Cauchy? Whenever you have a sequence where consecutive terms differ by something and the something forms a summable series, is a convergent series, then the original sequence is Cauchy. So this is again a property of Cauchy sequences. When you have a Cauchy sequence where consecutive terms differ by something less than the general term of a convergent series, then the original sequence is Cauchy. Try to prove this yourself. Therefore yk is Cauchy. So V is complete, and therefore yk will converge to y. And therefore you have, so let us, so now we have x and k plus w minus y plus w in v by w. This is less than or equal to any element in each of these sets, therefore norm of yk minus y, and that goes to 0. And therefore x and k plus w converges to therefore we have produced a subsequence which is convergent. Again, you have a Cauchy sequence property. If you have a subsequence converges in a Cauchy sequence, then the original sequence also converges to the same limit. Therefore, so this implies that xn plus w also converges to y plus w. So we have used three properties of Cauchy sequences, namely, and you should check them all. First is, in a Cauchy sequence, consecutive terms can be made to differ using a subsequence. You can find a subsequence such that consecutive terms differ by whatever quantity you decide. Now, if a sequence has consecutive terms differing by a general term of a convergent series, then the sequence is Cauchy. And thirdly, if you have a Cauchy sequence and you have a convergent subsequence, the sequence converges to the same limit. So using these three, we have shown that if V is complete, then V by W is also complete, and therefore it becomes a Banach space. So with these examples, we will wind up, and then we will our next topic for discussion will be continuous linear transformations. Thank you.